So we're going to kind of move into this idea of, we're going to be interested in not necessarily what the actual sum of a series adds up to. Sometimes we will be for certain special series, but just the idea of, does it converge or does it diverge, and can we prove it one way or the other, okay? So we're going to learn a whole bunch of tests. Right now we only have the test for divergence, which is, just to remind you because it's been a while, a series, right, is just this. Oh, okay, Siri, you're going to come up. Very good. A series is just the sum of the terms of a sequence, right? So it's this, which is A1 plus A2 plus A3 out to infinity. And we found that the test for divergence, does anybody remember what it was? So it's if the limit of the corresponding sequence being just an, right? If that's not 0, then sigma an diverges. And the idea there is basically what we're saying: if the terms aren't getting smaller and smaller, if they're not getting smaller and smaller, they're either staying constant or approaching some finite value, then you're just going to keep adding on to an infinite sum in increments that'll diverge towards infinity. It'll make the sum add up towards infinity, right? All right, but remember that the converse of that statement isn't true necessarily. So it is necessary for an to go to 0, but not sufficient for convergence. And what I mean by that is, yes, for the overall series to be convergent, the corresponding sequence has to approach 0, but just because the corresponding sequence approaches 0 doesn't necessarily mean the series is convergent. We saw that for the harmonic series. So that's sigma 1 over n, right? And we saw that that diverges, even though the limit as n approaches infinity of 1 over n goes to 0, sigma 1 over n still diverges, right? Okay. A little summary of kind of what we did in 11.2, or part of what we did in 11.2. All right, so right now that's really our only test for convergence or divergence, is the test for divergence. And then the only other thing we really truly have is if it's a geometric sequence, we know when it's convergent, and we also know how to find the sum when it's convergent. We have a formula for that. And other than that, we did a couple of special series by inspection. Like we had that telescoping series that we showed collapses down, and we found the sum of that. But no other test. So today we're going to learn a new test for convergence called the integral test. All right, so we're going to start here, and we're going to investigate 1 over n squared. So just looking at the first few terms, we get 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. So one thing I can do, let's sketch this out. Let's sketch out the function, let f of x equal 1 over x squared. And what I'm going to do is sketch out this function and sort of try and find a geometric representation of the series that we have. So 1 over x squared has two branches. It has a branch on either side of the y-axis, but we only need the positive side, so I'm only going to look at this branch. And the y-axis is an asymptote, and the x-axis is also an asymptote, right? All right. And let's look at the first few points. So I'll look at 1, 2, 3, 4, and 5. And we could continue on like this, but I just want to show something. Which is, all right, if I draw a straight line up to here, and I make a right endpoint rectangle, so meaning it's a rectangle where I'm using the right side of that bottom subinterval to represent the height of the rectangle. What's the height of that rectangle? What's that y value there? Specifically, it's 1 over 1 squared, right? If I do the same thing here, what's the height of this rectangle? 1 over 2 squared. One over 3 squared, and so on, right? Now the width of these rectangles is what? So the areas actually correspond to the terms in that sequence, in that series rather, right? Like this first area is just 1 over 1 squared, because it's 1 over 1 squared times 1. And then this area would be 1 over 2 squared times 1, which is 1 over 2 squared. And this area would be 1 over 3 squared times 1, which is 1 over 3 squared. And this area would be 1 over 4 squared times 1. And that would be 1 over 5 squared minus 1. And so on, right? Are these an underestimate or an overestimate of, would you say, the area under the curve? Underestimate, okay. So if we can show, and I don't want to go from 0 to infinity because I have two asymptotes here, but would you agree that this is going to be less than, the sum of these is going to be less than or equal to, I don't need the or equal to, it's clearly specifically less than, the sum, I'm going to just take the first rectangle, which is 1 over 1 squared, and then I'm going to add the area from here on. Now that would be the integral from 1 to infinity of 1 over x squared dx. Yeah? So if I can show if this converges, if that's convergent, meaning converges to a value, and we said that our sum is going to be smaller than that, then we must have proven that our sum has to converge as well. Do you agree with that? Because if our sum is less than a finite value, it must also be finite, right? That makes sense to everybody? All right, well this guy here is just an improper integral. We know how to deal with that. This term is just 1. So I'm going to just say it's 1 plus And remember how we deal with an improper integral. You're going to replace it with a variable. So it's an infinite limit. I'll just replace it with like t. And I'll take the limit as t approaches infinity. I'm going to rewrite that as just x to the negative 2, so I can use the power rule. All right, what's the antiderivative of x to the negative 2? Whoa, not everybody at once. Antiderivative of x to the negative 2. You could just use the power rule, right? Add 1, divide by the new exponent. What's negative 2 plus 1? And then divide by negative 1. So negative or negative 1 over x, right? I'm going to go from 1 to t. All right, so it's 1 plus the limit as t goes to infinity of negative 1 over t, and it's going to end up being plus 1. All right, so now let's apply our limit. What does negative 1 over t do as t approaches infinity? That's going to go to 0. And so we're just going to have 1 plus 1, which is 2, right? All right, so what we're saying is that the area that I shaded in red plus this one rectangle converges to 2. Now, does that mean our sequence converges to 2? No. Our sequence was represented just by the area of the rectangles, right? This is more than the area of the rectangles, right? But what it does prove, so our series doesn't converge to 2. But we've proven that the area under this curve from 1 to infinity plus the area of that first rectangle, that's going to be bigger than the sum of our series, right? And that converges to 2. Therefore, our series must be convergent. It must add up to a finite value. So let me draw these in one more time. Remember that we represented our series geometrically as the sum of the area of these rectangles, right? And then you agreed with me that the sum of the area of those rectangles are going to be less than the area under this curve because we have these gaps, right? All right. Well, if the area under that curve is finite, it must be true that the area of the rectangles is also finite, right? And the rectangles are actually just a geometric interpretation of that series. So here's the takeaway from this. What I'm going to show you is the first thing you have to do is have a conjecture about whether you think the series is going to converge or diverge. If you think it is convergent, like this one, what you want to do is come up with a geometric representation like we did, such that the area under the curve will be more than the geometric area of your representation, right? And then show that the area under the curve is convergent. So the geometric representation, so these rectangles, the area of these rectangles must also converge. So now we're going to do the opposite. I'll try and do this a little cleaner. All right, so yeah, this is kind of a cleaner version of that. The sum of those rectangles is a geometric representation of our series. The sum of those rectangles is definitely less than the first rectangle plus the total area under the curve from 1 to infinity. And we showed that that area converges to 2, which proves that our sum, our infinite sum, must be less than 2. If it's less than 2, it's convergent. You can't have something be infinite but also less than a finite value. All right. So now let's investigate. Let's do the opposite. So I'm actually going to draw this out. Let's look at the series sigma from I equals I'll say from n equals 1 to infinity of 1 over the square root of n. Okay, so now I'm looking at 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4 and so on. Now right away, if I didn't give you any information and I was just like, either prove that this is convergent or divergent, what we want to do is make a conjecture. And so we might start with our test for divergence, which is, let's look at the corresponding sequence, which is just what's in front of the sigma. Let's look at that, and let's let n approach infinity. All right, well, what does that sequence do as I let n approach infinity? The numerator stays constant. What does the denominator do? So what does the overall fraction approach? Okay. So the sequence approaches 0. Does that do anything for us? No. It still could be divergent. It still could be convergent. If it was non-zero, we could right away go, it's divergent, and we're done, right? But it's 0, so it could still be either. So now I want you to make a conjecture. We saw in the last example that sigma 1 over n squared does converge. And all that means is that these terms get small quickly enough that an infinite number of them are going to add up to a finite value, okay? But we saw that the harmonic series last time, which is sigma 1 over n, actually diverges. Which means even though the terms get smaller progressively, they're not getting small fast enough to add up to a finite value. They actually add up to infinity. What's your conjecture about how quickly the terms in 1 over the square root of n get small? Do you think they get small fast enough to converge? Or do you think they get small? Probably diverge, because they get small less quickly than the harmonic series, right? All right, so we have our conjecture. We think it diverges. So now what we want to do is come up with a geometric representation, but in the opposite way. We want our rectangles basically to overlap our curve. Okay? So let's let f of x equal 1 over the square root of x. This looks very, very similar to our last graph. It's just going to approach the x-axis more slowly. It's going to be like, it's still getting close to the x-axis, but just a lot slower. And we're still going to look at like the points 1, 2, 3, 4, and so on. But now when I make my rectangles, I want to make them so that they overlap the curve. So in this case, I'm going to go up from 1. And I'm going to draw my rectangle to the right. All right, what is the area of that rectangle? Well, its height here will be what? What's that y value? 1 over rad 1. And its base width is also 1, right? So its total area is also the 1 over rad 1. So the area of that rectangle represents the first term in our series. And then I'll just move on from there. Second rectangle here. That height is 1 over rad 2, so its area is 1 over rad 2. This height is 1 over rad 3, so its area is also 1 over rad 3 because the base is a width of 1. We could continue this. So if I add up these rectangles, that's just the geometric interpretation of my series, right? And we thought it's divergent, which is why I decided to make them such that they were overlapping the actual curve. Because what my goal then is going to be to show, if I can show the area from here to infinity is infinite, and the area of the sum of our rectangles is bigger than that, then the area of the sum of the rectangles also has to be infinite, right? And thus the series diverges, which is what you guys conjectured, okay? And so we're going to do the same thing. So I'll say that that series, the sum of that series from n equals 1 to infinity of 1 over root n is definitely less than, how would you set up the integral for that curve? What integral am I looking at here? I want the area of the shaded region. So what does my integral look like? Here, I'll start. The integral. What's my lower limit of integration? Of the function, which is 1 over root x dx, right? Okay, so we know that the sum of our series, oh, I wrote that backwards, and I apologize, folks, is, in this case, it's greater than that. We're proving divergence. So we can definitely see that the rectangles overlap that area, so there's going to be more area in the rectangles than there is in the shaded green. All right, so now let's just work on evaluating the integral. So the integral, I'll take the limit as t goes to infinity from 1 to t, and then I can just kind of clean up. 1 over root x is the same as x to the negative 1/2 dx. All right, so let's find an antiderivative. So if I add 1 to negative 1/2, I get positive 1/2, yeah? And then if I divide by that new exponent, dividing by 1/2 is the same as multiplying by 2. That's from 1 to t. All right, so finally, what I have is the limit as t approaches infinity. X to the 1/2 is the same as the square root, so that's 2 root t minus 2. Okay. Well, as t goes to infinity, what does the square root of t go to? it just gets larger and larger. The square root of t, it's going to get larger and larger slowly, but it doesn't approach anything, right? It just continues to get larger. So this goes to infinity. Infinity minus 2, which is still infinity, right? So what we've shown then is that sigma 1 over root n is greater than infinity. Well, what's greater than infinity? More infinities, right? So therefore it diverges. Divergence. All right, so this is the gist of the integral test. Suppose you have a continuous positive decreasing function on the interval from 1 to infinity and let your sequence a of n equal f of n. Then the series sigma an is convergent if and only if the proper integral is convergent. In other words, if the integral from 1 to infinity is convergent, then sigma an is convergent. If the integral from 1 to infinity is divergent, then sigma an is divergent. So you don't have to go through making that geometric representation every time. I just did it the first 2 times to show you why it will work. You do need to know, to use the integral test, your corresponding series has to decrease, right? Sorry, your corresponding sequence has to decrease rather, but that's always necessary for convergence. And so one quick note, and that'll help with series like this, it's not necessary to start the series integral at 1, because a finite number of terms aren't going to ever make the difference between convergent or divergent, right? If all you're doing is adding a finite number of terms to a convergent series, it's still convergent. It's still going to add up to a finite value. And so that helps here because this has a vertical asymptote at x equals 3. And so if you were trying to integrate that from 1 to infinity, you'd have to break it up into 2 separate integrals because there's an asymptote at 3. So instead, you can avoid that by going from 4 to infinity and then just recognizing, okay, well, I didn't add up the first 3 terms, so I'll just add those at the end, and that's not going to change convergence or divergence. All right. No. All right, so test the series for convergence or divergence. So we learned that all we need to do is verify that it's a decreasing sequence. It's pretty clear that this sequence is decreasing because if we take the limit as n approaches infinity of the actual sequence, so of the 1 over n squared plus 1, so what I would do is just divide everything by n squared, top and bottom. So that's going to give me 1 over n squared over 1 plus 1 over n squared. And then the 1 over n squared terms go to 0. The 1 stays a 1. And we can see that that sequence approaches 0, which means the terms must be getting smaller, right? Must be decreasing in that case. All right, so once we know that the terms are approaching 0, we're just going to let a function, a continuous function, equal 1 over 1 plus x squared. Or sorry, x squared plus 1, I guess they're equivalent. And then I'm going to look at the integral from 1 to infinity of 1 over x squared plus 1 dx. And the integral test just says if that converges, the series converges. If this diverges, the series diverges. Okay, so we'll let t go to infinity, and I'll look at the integral from 1 to t of 1 over x squared plus 1 dx. All right, this is an antiderivative that we know. Does anybody remember it? The derivative of something equals 1 over x squared plus 1. It's arctan, or inverse tan. All right, I have the limit as t approaches infinity of inverse tan of t minus inverse tan of 1. So let's think about what inverse tangent does as its input approaches infinity. So tangent looks like this, negative pi over 2 to pi over 2. Right? So inverse tangent just gets reflected over the line y equals x, so it's going to invert the asymptotes. Basically sends them to the x-axis like that. It's going to look like a reflection over the line y equals x. So as we let our input go to infinity, so as we approach infinity on the x-axis, what are our outputs approaching? Pi over 2. So I end up with pi over 2 minus inverse tangent at 1. Whatever that is, it's just a constant, right? So pi over 2 minus a constant is still just some constant. So this series converges, right? So because this test has a name, you need to finish it off with therefore the series converges by the integral test. All right, example 2, we did a couple of these, but I'm just going to give you the theorem, which is the P series, 1 over n to the P, is convergent if P is greater than 1, and is divergent if P is less than or equal to 1. So we already kind of saw that. We did a couple examples. We proved that the harmonic series, which is just the series 1 over n, is divergent. We proved that the series 1 over root n, which would actually be a P series with P as 1/2, 1 over p to the, or n to the 1/2, is divergent. And then we showed that 1 over n squared is convergent. And so it can actually be shown that if p is strictly greater than 1, then you have a convergent p series. And you can just quote that. You don't have to use the integral test or anything. So if you have something like, hey, is this convergent or divergent? You can go convergent because it's a p series with p equals 1.1, which is greater than 1. All right, here's just a quick example, couple p series. So a sigma 1 over n cubed, we can right away say it's convergent because it's a p series with p equal to 3, which is greater than 1, right? But the series 1 over n to the 1/3 is divergent because it's a p series with p equals 1/3, which is less than 1. And this is a note I already made. Remember, the integral test is not finding the sum of the series. It's either finding a sum that's greater than or less than the series. So just because the integral of 1 over x squared equals 1, that is not the sum of the series 1 over n squared. Euler proved that the sum of that is x squared over 6, and it's actually an insane proof. Which is obviously not 1. All right. I think that's plenty for today. We're going to actually hold off on example 4 and the remainder test